Hi everyone, welcome to another episode of learning about construction and engineering with the merchant construct-preneurs and tutors. Before we go ahead, kindly click on the like button, share and also subscribe to this channel, the merchant construct-preneurs and tutors. Today we'll be looking at the simplified explanations of reinforced concrete beam sections and supports. So, reinforced concrete is a composite type of structure that is made up of steel, reinforcement, and also concrete. So, we are looking at the beam itself. So, from here, my definition here, I have a beam is simply a horizontal structural member in the structure that is designed to resist bending and other structural stresses. Now, it supports the weight and also transfers the weight to the vertical structures below it to ensure stability and safety of buildings and other structures. What this is saying is, typically or usually the beam is always sitting on a vertical member. Since it's an horizontal member, it's sitting on a vertical member, and that vertical member can be reinforced concrete wall or columns itself. So it transfers the weight of whatever that is on top of it, whether brick wall, slab, it transfers it down to the vertical member, the columns, and then down to the foundation and then to the floor. So another definition of a reinforced concrete beam, you can define it based on three categories. Now you have the shape and cross section, we have the position of the reinforcement, and also we have the support conditions. So we'll be taking these classifications bit by bit or one after the other so that we have a clear understanding of what a beam is and how to describe it for reinforced concrete beams. So the first one under classification based on cross section, we have the rectangular section, and that's the cross section there. We have the T section. Now this T section is slab is incorporated in it, in which the beam is in between and then the slab. Then the L section is always at the edge of the slab or the structure. So the slab takes part and then the other part is the beam, but the beam enters into the slab or the slab enters into the beam. Let me use that word. The slab and the beam are interwoven. Then the second classification, this is classification based on the position of the reinforcements. No, the first one we already did that based on cross section. Now this one, position of the reinforcements. And for a beam section, we have what is called the neutral axis. We have the upper part is called the compression area, and then the lower part is the tension area. So if the reinforcement is placed below the neutral axis, that is at the tension area, the beam section is said to be singly reinforced. You get that? So if the reinforcement is at the bottom, then you have a beam, the reinforcement is at the bottom. It is designed to be at the bottom. That is singly reinforced. It doesn't mean that reinforcement is not going to be at the top, but those ones at the top are just to complete the shape. You can't leave it hanging like that. So, but the ones that are actually designed for are the ones at the bottom. So if the design you have carried out is just at the bottom, then it is singly reinforced. Or when the design moment is less than the ultimate moment. Now we know about our stress-strain relationship. You know what the ultimate stress is. So if at the ultimate, after the ultimate point, we have the breaking point, we have the yield, then it goes to the ultimate. So if whatever you have designed is less than the ultimate, so it is singly reinforced. So the diagrammatic illustration of what I'm saying is from the diagram shown here. We have that middle line as a neutral axis, you have the width, then D is the effective depth to the tension reinforcement, X is distance to the neutral axis. So for the second part of the classification based on the position of the reinforcement. Now, if the reinforcement is placed at the compression area that is above the neutral axis and also at the tension area below the neutral axis. You know, from the I'm using the rectangular section as an example to describe whatever I am saying now. So the rectangular section, if you divide at the center is the neutral axis. Above to the top there is the compression area, while below to the bottom is the tension area. So if the reinforcement is placed both at the top and bottom, it is designed top and bottom, it is doubly reinforced. Also, when the design moment is greater than the ultimate moment, the beam section should be designed as doubly reinforced. The beam section should be designed as doubly reinforced, because once anything has passed the ultimate moment, the next point is the breaking point. So if your design moment is already higher than the ultimate, then you just have to provide the reinforcement at the top, and that reinforcement at the top is to resist those moments and then bring it back to normal. So the first one, singly reinforced, you design the reinforcement for the bottom only. The bottom tension area can actually cater for the design and the ultimate moment, comparing the design moment to the ultimate moment. But for this one, this doubly reinforced, the bottom alone cannot do it, so we have to introduce the top. So for this section now, looking at it, we have the B as the width, D as the effective depth to tension reinforcement, effective depth to compression reinforcement is the D prime, if you look at it from the diagram there. So we also have the AS prime is for the area of steel for the compression reinforcement. So you start from the middle, just the area at the top there. Then the AS is the area of steel for the tension reinforcement. I hope we understand what I'm saying. So it is easier to be able to differentiate between singly reinforced and doubly reinforced. Now looking at the third classification, based on the support condition, simply supported. When it is supported at two ends, one side is pinned, the other side is roller. So it allows for rotation and translational movements, as shown in the diagram. Then for the second part, based on the support conditions, we have three classifications: cross section, we have the cross section, position reinforcement, and then the support condition. So the third one, that's what we're looking at, and then we have the simply supported, which I already explained. Now the continuous beam. This is the beam that is supported by more than two supports, offering greater stability and load distribution. It is mostly used in bridge construction, just as you can see in the diagram. So the supports are there, but they are simply supported. So solving something like that, you need to treat each section separately, simply supported, so it will be easier to resolve. Now the third part of the classification based on the support conditions is the cantilever beam. Now this is the beam that is supported only on one end, and then with a fixed support and the other end free. It is common in balconies and overhanging structures. So as you can see in the diagram, it is fixed on one side and the other end is free. So that is what we call the cantilever beam. Now for the next one, we have the fixed beam. This is the beam that is supported on both ends with restrictions to rotation and translational movement. So for the diagram, it is fixed on both ends, so it doesn't allow for any form of movement at all. It is fixed. Totally no form of movement at all is allowed. So we are going to be looking at the functions of reinforced concrete beam. What it actually does in the structure. We defined what beam is and reinforced concrete beam, and then the classification. Now what exactly does this thing do? Now the first one, we are looking at load bearing. Now reinforced concrete beams are designed to support the weight or loads of elements above it, such as the floor, roof, slab, etc. We also have walls, block walls. So anything that's above the beams support it. It bears the load. Now the second part of it now, it is load distribution. After collecting the load, it transfers it down to the next vertical element below it. So the reinforced concrete beams are designed to distribute load safely to its end and then down to the vertical support. So when you have a stretch of beam, to prevent structural failure and maintain stability, when you have a stretch of beam, as it is receiving the load, it is transferring the load to the nearest support, then taking it down, it's transferred safely. So we have mentioned two functions, load bearing one, then load distribution. Then the third one is the resistance to bending moments and shear force. Now, reinforced concrete beams are designed to resist bending caused by external loads that induces bending. What this means is, as the loads are on top, whether for walls or anything that the beam is bearing, at the center, when you have a beam, if the slender, once you apply load at the center, is going to tend to bend. So the beam his work is to resist it. Then shear force, the internal forces, since the load is already acting on it, the reaction to this thing that will allow this thing to shear, it wants to give way. So the reinforced concrete beam actually prevents that. So I believe you got value for this. Please kindly